Something happened to the sonar systems monitoring the deepest section of the Pacific Ocean 11 days ago, and the explanation that federal agencies have offered does not hold up against the data. Not partially, not in the details. It does not hold up at all. At 3:14 in the morning Pacific Standard Time, on a date that has now been confirmed by 3 independent monitoring stations operating under 3 separate institutional frameworks, every active sonar return from a specific section of the Abyssal Pacific, a section covering an area larger than the state of Texas, went dark simultaneously. Not degraded, not reduced, not intermittent in the way that equipment failures tend to produce, with partial signal loss and erratic readings that point toward a mechanical or software explanation. Dark, as in the acoustic energy that the monitoring systems were sending down into the water column stopped coming back. As in, something in that section of the ocean, between the surface and the seafloor at depths between 3,800 and 6,200 meters, began absorbing or deflecting sonar returns in a way that produced, on every instrument trained at that region in that 11-day window, an absence where there should have been data. The official explanation, issued by the National Oceanic and Atmospheric Administration 14 hours after the anomaly was first logged internally, attributed the loss of sonar return to a combination of deep-water thermocline disruption and instrument calibration variance. Researchers who have spent careers studying deep-water acoustic propagation read that statement and reached for their phones. Not because they had answers, because they recognized immediately that the explanation offered was not capable of producing what the data described, and that someone either did not understand what had happened or did not want to say what had happened, and neither of those possibilities was comfortable. The thermocline, that boundary layer between warmer surface water and colder deep water, where the temperature gradient bends sound waves and affects acoustic propagation, does cause sonar interference. This is documented, well-understood physics. But thermocline disruption does not cause simultaneous total signal loss across an area the size of Texas on every monitoring system simultaneously. It causes regional variations. It causes depth-dependent effects. It causes the kind of gradual, geographically patchy signal degradation that oceanographers deal with routinely, and that every sonar operator in the field knows how to account for. It does not cause every instrument pointed at a defined geographic region to return nothing at the same moment. That is not thermocline physics. That is something else, and the gap between the official explanation and what the data actually shows is the beginning of this story, not the end of it. What makes the gap more significant, rather than less, is what was happening in the target region in the weeks before the sonar systems went dark, because the darkness did not arrive without warning. There were signals, and the signals were being watched by people who understood what they were looking at, and those people are now being very careful about what they say publicly, in the specific way that scientists are careful when the thing they are looking at does not have a place in the existing literature, and they are not yet certain whether that is because the thing is genuinely new or because they are missing something obvious. That careful, precise, professionally cautious silence is louder than most announcements, and it is the sound that this story is built around. Before the sonar went dark, 3 separate research groups operating in the Pacific had logged anomalous readings in the target region over a period of approximately 6 weeks. The anomalies were different in character. One group was tracking unusual water column stratification patterns using Argo float data. A second group, working out of a university oceanography department in Japan, had noticed something in the deep current velocity measurements from a moored instrument array they maintain at the western edge of the target region. And a third group, an independent research team similar in profile to the one that identified the acoustic anomaly in last year's Central Pacific investigation, had been analyzing hydrophone data and had filed a preliminary report with NOAA describing what they characterized as a large-scale acoustic scattering event beginning at depths consistent with the boundary between the mesopelagic and bathypelagic zones, approximately 1,000 meters, and extending downward into the abyssal layer. 3 groups, 3 different instruments, 3 different institutional affiliations, all looking at the same region of ocean, all finding something that did not fit the expected behavior of that section of the Pacific. And then, on the 11th day of the current month, every sonar system trained on that region went simultaneously dark, and the official explanation arrived 14 hours later, and the researchers who had been watching the anomalies in the weeks before went quiet in the careful way that means the opposite of nothing to see here. The Pacific is the largest ocean on Earth, covering more than a third of the planet's total surface area. Its abyssal zone, the region below 4,000 meters, encompasses an area that dwarfs every continent except Asia. It is monitored by an infrastructure that is impressive relative to what existed 50 years ago and grossly insufficient relative to the scale and dynamism of the system it is supposed to observe. The target region, where the sonar systems went dark, sits in the Central Pacific, in a section of the abyssal plain that has historically been considered among the most geologically and oceanographically quiescent parts of the entire basin. Quiescent meaning nothing much happens there. The seafloor is flat. The geological activity is minimal. The biological productivity in the overlying water column is low, because the Central Pacific is an oligotrophic gyre, a slow-moving circulation system where nutrient-poor water produces relatively little life compared to the more productive margins and upwelling zones. It is, in short, the kind of place that monitoring systems are not optimized for, because the assumption embedded in the design of those systems is that the interesting things, the things worth watching closely, happen elsewhere. That assumption may now need revision. Stay with this, because what the data shows from the 6 weeks before the blackout and what the absence of sonar returns since the blackout implies about what might be happening in 6,200 meters of dark Pacific water right now is the kind of story that does not resolve cleanly into a headline, and that is exactly why it matters. The 3 research groups whose anomalous readings preceded the sonar blackout did not know about each other until after the blackout occurred. That detail is important because it eliminates the possibility that the pre-blackout data represents a coordinated interpretation, a shared analytical framework producing similar conclusions from similar assumptions. These were independent observations, made with different instruments, processed through different analytical pipelines, by researchers with different training and different institutional contexts, who arrived at similar conclusions about the same region of ocean without any communication between them. The convergence of independent observations on the same geographic target is one of the strongest signals in science that something real is happening in that location, as opposed to something being produced by a shared methodological bias or a shared instrumental artifact. When 3 groups looking at the same place with different eyes all see something unusual, the unusual thing is probably there. The first group, the one tracking water column stratification using Argo float data, noticed the anomaly approximately 6 weeks before the blackout. What they observed was a disruption in the expected density structure of the water column in the target region. The ocean's water column is stratified by density, which is itself a function of temperature and salinity. Denser water sits below less dense water, and the gradients between layers are generally stable on the timescales relevant to routine oceanographic monitoring. What the Argo floats in the target region began recording 6 weeks before the blackout was a compression of the deep density layers, a squeezing of the normal vertical spacing between density surfaces that is consistent with either a large-scale vertical movement of water masses or a change in the temperature salinity properties of the water at depth sufficient to alter its density structure. Either interpretation is significant. Large-scale vertical movement of deep water masses in the Central Pacific Gyre is not a routine occurrence. The gyre circulation is predominantly horizontal, driven by wind stress at the surface and propagated downward through a complex of geostrophic and ageostrophic dynamics. Vertical movement of the scale implied by the density layer compression seen in the Argo data would require a forcing mechanism that is not part of the normal circulation pattern of that region, and no known atmospheric or oceanographic forcing was operating in the target region during the relevant period that would account for it. The change in temperature salinity properties interpretation is equally troubling because the deep water masses of the Central Pacific are among the most stable and slowly evolving water bodies on Earth. They are formed at high latitudes, where cold surface water sinks and spreads equatorward along density surfaces over periods of decades to centuries, and they maintain their properties with remarkable fidelity over the enormous geographic distances they traverse. A change in their temperature salinity signature in a specific region, detectable over a period of weeks, implies a local modification process of unusual intensity, and the location of the modification, deep in the abyssal Pacific, places it outside the reach of the surface-driven processes that normally modify ocean water masses. Something below was changing the water above it, or something was moving through the water column from below, and the Argo floats were catching the edges of it. The second group, the Japanese team monitoring deep current velocities from their moored instrument array at the western edge of the target region, observed something different but complementary. Current meters deployed at depths between 3,000 and 4,500 meters began recording velocity anomalies approximately 5 weeks before the blackout, slightly later than the density anomalies seen in the Argo data. The anomalies were not large in absolute terms. We are talking about current speed departures of a few centimeters per second from the climatological mean, which in the context of deep ocean currents, where typical velocities are already measured in centimeters per second, represents a meaningful fractional change. What made the velocity anomalies notable was not their magnitude, but their spatial coherence. Current meters at different depths and different horizontal positions within the array were all showing anomalies with similar timing and similar directional character, as if a coherent flow feature of large horizontal scale was moving through the array from a direction inconsistent with the normal deep circulation pattern of the region. The flow direction implied by the anomalies was predominantly upward and outward from the center of the target region. Not uniformly, not cleanly, but with a statistical tendency that the Japanese team's principal investigator described in a message to a colleague, a message that has since been shared within the research community, as resembling the outward spreading flow you would expect at the base of a large-scale upwelling plume. A deep water upwelling plume in the Central Pacific Abyssal Plain. That phrase, assembled from the current meter data of a monitoring array installed for entirely different purposes, represents one of those observations that causes a scientist to sit very still and look at the data a second time and then a third time before saying it out loud, because what it implies about what is driving it does not have an obvious conventional explanation. Upwelling in the ocean is a real and important process, but it is a surface and coastal phenomenon driven by wind stress and Coriolis effects. Deep water upwelling of the character implied by the current meter data, originating at abyssal depths in the middle of the largest ocean on Earth, driven by something that is pushing water upward and outward from below, is not a feature of the normal circulation models for that basin. The third group's hydrophone findings added the acoustic dimension to what was already a multi-instrument anomaly. Their characterization of a large-scale acoustic scattering event, beginning at approximately 1,000 meters depth and extending downward, was based on an analysis technique called acoustic backscatter profiling, in which the intensity of sound returned to a transducer from different depths in the water column is used to infer the distribution of scattering objects, which can include biological organisms, suspended particles, gas bubbles, or density discontinuities in the water. What the third group found was a scattering layer of unusual depth extent and unusual intensity, beginning at the base of the mesopelagic zone and continuing downward through the bathypelagic and into the upper abyssal depth range. Normal deep scattering layers, the biological communities of fish, crustaceans, and gelatinous organisms that perform the Deal vertical migration every night, occupy the upper few hundred meters of the water column and have well-characterized acoustic signatures. What the third group was seeing extended far below the normal deep scattering layer depth range and had spectral characteristics inconsistent with the known signatures of any biological scattering layer previously documented in the scientific literature. Something in the water column of the target region, from 1,000 meters down into the abyss, was scattering acoustic energy differently than anything that had been recorded there before. When all three data streams are laid alongside each other, the density anomaly from the Argo floats, the deep current velocity anomaly from the Japanese mooring array, and the deep acoustic scattering anomaly from the hydrophone analysis, and when the timeline of each is mapped against the others, a coherent picture begins to assemble. The density anomaly appeared first, approximately 6 weeks before the blackout. The current velocity anomaly appeared approximately a week later. The acoustic scattering anomaly was first noted approximately 3 weeks before the blackout and was described as intensifying in the days immediately before the sonar systems went dark. The sequence is consistent with a process building over time, starting with a change in the deep water column properties, progressing to measurable changes in deep circulation, and culminating in a large-scale acoustic phenomenon of sufficient intensity to absorb or deflect the sonar returns of every monitoring system trained on the region. The sequence is consistent, but consistent with what is the question that nobody is yet prepared to answer in print. The moment the sonar systems went dark, the operational response from the agencies responsible for monitoring that section of the Pacific followed a pattern that is familiar to anyone who has studied how federal science agencies handle anomalous events that fall outside their established response frameworks. The pattern is not sinister in its design. It is bureaucratic in the most literal sense. It reflects the behavior of large institutions that were built to manage known categories of events, and that, when confronted with something that does not fit a known category, default to the procedures that exist rather than improvising procedures that don't. The first response was internal flagging, the anomaly logged in the monitoring system's event record and elevated to the duty officer responsible for overnight operations. The second response was a check of instrument status, a verification that the sonar systems themselves had not experienced a technical failure. That check returned normal across all systems, meaning the instruments were functioning, powered, and transmitting, and the absence of return signal was not a hardware problem. The third response was a request for confirmation from adjacent monitoring assets, asking whether systems at the edges of the target region were showing similar signal loss, or whether the blackout was geographically contained. The confirmation came back within 2 hours. The blackout was geographically contained, with a relatively sharp boundary at the edges of the target region, beyond which sonar returns were normal, and a total absence of return within the target area that was consistent across every depth layer from the surface to the maximum operating depth of the systems involved. a geographically contained, depth-spanning, simultaneous, total sonar blackout with no instrument malfunction. That combination of characteristics does not appear in the Standard Event Response Playbook because the Standard Event Response Playbook was not written with that combination in mind. The fourth response, which came approximately 6 hours after the initial logging of the anomaly, was a request for consultation with the Naval Oceanographic Office, which maintains its own suite of acoustic monitoring assets in the Pacific, and which has both the technical expertise and the operational mandate to evaluate acoustic anomalies in that basin. The Naval Oceanographic Office responded to the consultation request, and what they said in response has not been made public, but the fact that the consultation was requested and that the official public statement from NOAA followed 8 hours after the naval consultation, with an explanation attributing the blackout to thermocline disruption and instrument calibration variance, is a sequence that researchers familiar with how these agencies communicate with each other have found notable. Not because a naval consultation is unusual, it is a normal part of how civilian ocean monitoring agencies handle events with potential security implications, but because the public explanation that followed the consultation was, in the assessment of multiple independent experts, inadequate to the data. The thermocline disruption explanation, to be precise about why it fails, requires that a thermocline disturbance of sufficient intensity to completely block sonar returns across an area larger than Texas formed spontaneously, persisted for more than 11 days, maintained a relatively sharp geographic boundary, affected all depth layers simultaneously, and did so without any associated atmospheric forcing, without any anomalous surface signature visible in satellite sea surface temperature data, and without any prior indication in the surface meteorological record that the kind of storm or atmospheric event capable of driving a thermocline disruption of that scale had occurred in the target region in the preceding days or weeks. None of those conditions were met. The satellite sea surface temperature data for the target region shows no anomaly consistent with a major thermocline disruption event. The surface meteorological record is unremarkable. There was no storm, no atmospheric forcing, no surface signature of the kind of energy input that would be required to drive a subsurface acoustic event of this character from above. Whatever is causing the sonar blackout is not being driven from the surface. It is coming from below, and the official explanation, which describes a surface-driven process, is not consistent with the evidence. The instrument calibration variance portion of the official explanation fails on different grounds. Calibration variance in sonar systems produces instrument-specific signal degradation that varies between systems based on the individual calibration state of each instrument. It does not produce simultaneous, identical signal loss across multiple systems operated by different institutions using different hardware maintained under different calibration schedules. The probability of a calibration variance event producing simultaneously identical total signal loss across every monitoring asset in a defined geographic region is, in the careful language of statistical analysis, vanishingly small. In plain language, it did not happen. The researchers who have examined the event data are not claiming to know what caused the blackout. They are claiming with considerable confidence that the official explanation does not describe what caused it, and that the gap between the explanation offered and the data available is large enough and structured enough to suggest that the explanation was not constructed from the data, but rather selected for its adequacy as a public communication, its capacity to provide a plausible-sounding reason for the anomaly without requiring further public discussion of it. That is a serious claim. It is being made seriously by serious people on the basis of specific technical analysis, not on the basis of general suspicion or institutional mistrust. And it is being made in the careful, qualified, professionally cautious language of scientists who understand that the claim they are making, that a federal agency issued a public explanation for a major oceanographic anomaly that the data does not support, carries professional and institutional weight that requires them to be precise and thorough in their reasoning before they commit to it publicly. They are committed to it. The data, they say, does not support the explanation. The explanation does not fit the event. And the event, whatever its cause, is still ongoing. The sonar systems are still dark. 11 days and counting, the target region of the Central Pacific Abyssal Zone is still not returning acoustic signals to the monitoring infrastructure trained on it, and the official position remains that this is attributable to thermocline disruption and calibration variance, and the researchers who know what thermocline disruption and calibration variance actually look like in acoustic monitoring data are watching a region of ocean the size of Texas that has gone completely silent and trying to decide what the silence means. The silence itself is data. In oceanographic acoustics, the absence of a return signal is not neutral. It is informative. A sonar system sends acoustic energy into the water column and waits for that energy to return, reflected and scattered by whatever is in the water. Biological organisms, suspended particles, density gradients, the seafloor itself. The total absence of return implies that one of several things is happening. The acoustic energy is being absorbed before it can return, which requires a medium of extraordinary absorption capacity that does not correspond to any known property of seawater at any temperature, salinity, or pressure combination found in the natural ocean. Or the acoustic energy is being scattered so diffusely that no coherent return reaches the receiver, which requires a scattering medium of extraordinary density and spatial extent distributed throughout the entire water column of an area larger than Texas. Or the acoustic energy is being deflected, redirected away from the receiving transducers by a refractive structure in the water column of sufficient curvature and spatial scale to bend the sound away from its return path. Each of these possibilities implies something about the physical state of the water column in the target region that is, in its own way, extraordinary. None of them corresponds to thermocline disruption as that phenomenon is understood in the oceanographic literature. And the fact that all three are being seriously considered by researchers who have examined the data tells you something about how far outside the normal parameter space this event is sitting. The physical oceanography of what could produce a sonar-absorbing, scatter-diffusing, or signal-deflecting water column condition across an area the size of Texas in the Central Pacific Abyssal Zone is not a question with many candidate answers, and working through the candidates carefully is the most important analytical step in understanding what the blackout data is actually telling us. Each candidate implies a different physical process, a different source, a different scale of energy input, and a different set of implications for what might be happening on and below the seafloor of the target region. The first candidate is a biological one, and it is the one that requires the least revision of existing frameworks while still being, in its own right, remarkable. The deep scattering layer, that community of mesopelagic organisms that performs the daily vertical migration, is one of the ocean's most important and least understood biological features. On a normal day, in a normal part of the ocean, the deep scattering layer produces a characteristic acoustic signature that sonar operators and oceanographers have been documenting and analyzing for decades. It attenuates sonar signals to a degree, particularly at frequencies used by certain military and commercial sonar systems, but it does not eliminate them. It does not produce total signal loss. However, the deep scattering layer, as it is normally understood, represents only the upper portion of the ocean's biological vertical distribution. The mesopelagic community, the organisms that constitute the normal deep scattering layer, live between approximately 200 and 1,000 meters. Below 1,000 meters, in the bathypelagic zone extending down to 4,000 meters, biological densities drop sharply. Below 4,000 meters, in the abyssal zone, they drop further still. The normal assumption is that biological scattering at abyssal depths is insufficient to produce meaningful sonar attenuation. But the normal assumption is based on normal biological densities, and the acoustic scattering anomaly identified by the third research group in the weeks before the blackout was characterized by unusual depth extent and unusual intensity, suggesting that something was present in the water column at depths where biological scattering is not normally significant. If the biological density in the target region's water column had somehow increased to levels far above normal across the full depth range from the mesopelagic to the abyssal, the acoustic consequences could theoretically approach what the sonar data describes. The word theoretically is doing significant work in that sentence. For biological scattering to produce total signal loss across the full depth range of the water column in an area larger than Texas, the biological densities required would be orders of magnitude above anything previously documented in the Central Pacific or in any comparably oligotrophic oceanic environment. The Central Pacific Gyre is one of the least biologically productive regions of the global ocean, precisely because it is nutrient-poor and isolated from the upwelling and mixing processes that drive productivity at ocean margins. It does not support the kind of biological abundance that would be required for biological scattering to explain the blackout. Unless something has changed the nutrient and productivity regime of that region dramatically and recently, which the pre-blackout anomaly data from the Argo floats and current meters does not obviously support, the biological candidate requires biological densities that are not consistent with the known ecology of the target region. It cannot be ruled out entirely because the deep ocean is, as has been established repeatedly, capable of containing biological communities that have not been previously documented, but it requires extraordinary biological conditions that have no precedent in the available data from that part of the ocean. The second candidate is geological, and it connects directly to the methane hydrate system that emerged as a central concern in the investigation of last year's Central Pacific acoustic anomaly. If a large-scale destabilization event in a deep methane hydrate deposit were releasing gas into the water column at a rate and over an area sufficient to create a persistent gas bubble layer throughout the water column, the acoustic consequences would be severe. Gas bubbles are extraordinarily effective acoustic scatterers and absorbers. A bubble resonates acoustically at a frequency determined by its size, and the distribution of bubble sizes in a gas-rich water column produces broadband acoustic attenuation that can, at sufficient bubble densities, approach total signal loss. The physics of gas bubble acoustic scattering is well understood and well documented, and it is one of the few physical mechanisms that is actually capable of producing the kind of total sonar blackout described in the event data. The question is whether a methane hydrate destabilization event of the scale required to produce persistent, area-wide total sonar blackout across an area larger than Texas is physically plausible given what is known about the hydrate inventory of the target region. The honest answer is that what is known about the hydrate inventory of the target region is not sufficient to answer that question confidently in either direction. The target region has not been the subject of systematic hydrate survey work. The existing estimates of hydrate distribution in the Central Pacific are based on indirect indicators, primarily bottom simulating reflectors visible in seismic surveys and thermal gradient modeling, and those estimates carry large uncertainties. What can be said is that the conditions in the target region, the depths, the sediment types, the thermal gradients, are consistent with the presence of hydrate deposits, and that the pre-blackout thermal anomaly identified in the Argo float data is consistent with a warming of the bottom water, sufficient to push hydrates near the boundary of their stability field toward destabilization. The thermal anomaly alone does not confirm hydrate destabilization, but it is consistent with it, and the combination of a thermal anomaly, a deep current anomaly suggesting upward fluid movement, a deep acoustic scattering anomaly, and then a total sonar blackout laid out in chronological sequence over a 6-week period, is consistent with a progressive hydrate destabilization event building from initial thermal perturbation through fluid mobilization to large-scale gas release. That sequence is not proof, it is a hypothesis. But it is a hypothesis that fits the available data better than the official explanation does, and it has implications that extend well beyond the acoustic monitoring problem into the chemistry of the water column, the biology of the deep ecosystem, and the carbon budget of the Pacific Basin. The third candidate is the one that the researchers involved are most reluctant to discuss publicly, not because it is implausible on physical grounds, but because the physical grounds on which it would be plausible require invoking processes that are not part of the standard oceanographic literature and that carry, in the current scientific culture, a burden of proof that the available data does not yet meet. That candidate is a large-scale, organized physical structure in the water column, not geological, not purely biological, but something that occupies the water column in a coherent, spatially organized way over an area of hundreds of thousands of square kilometers, and that interacts with acoustic energy in a manner that produces the observed blackout signature. The reason this candidate is being discussed at all, carefully and privately, by researchers who are accustomed to explaining ocean phenomena in terms of well-characterized physical and biological processes is that the spatial coherence of the blackout, its sharp geographic boundary, its uniform depth extent, and its persistence over 11 days without apparent change, is difficult to reconcile with either the biological or the geological candidate in their simple forms. Gas bubble clouds from hydrate destabilization do not normally maintain sharp geographic boundaries for 11 days. They disperse, they advect with currents, they change their spatial distribution as the gas rises through the water column and dissolves. A biological scattering feature of the required density would similarly disperse and evolve over 11 days under the influence of the currents and mixing processes operating in the target region. The spatial coherence and persistence of the blackout, more than its initial appearance, is what is driving the most careful and the most uncomfortable conversations among the researchers who are taking this data seriously. Something is maintaining that boundary. Something is keeping the acoustic darkness contained within a defined geographic region over a period of nearly 2 weeks. And the physical processes that are capable of maintaining a coherent, bounded, persistent feature of that scale in the deep Pacific water column are not numerous, and they are not all easily categorized within the existing frameworks of physical oceanography. The researchers who are circling this question are not claiming to know what the bounded, persistent feature is. They are claiming that its characteristics, its sharpness, its persistence, its depth extent, and its acoustic opacity constrain the set of possible explanations in ways that make some explanations more plausible than others, and that the most plausible explanations remaining after the less plausible ones are eliminated are the ones that are hardest to discuss in the language of established science. That difficulty is the most important thing about where this investigation currently stands. Before this story goes further into what the researchers are privately discussing and what the data constraints imply about the nature of the feature maintaining the blackout boundary, it is worth pausing to establish the full physical context of the target region, because the geography and geology of the seafloor beneath the dark water column is not incidental to the story. It is load-bearing. The section of the Central Pacific Abyssal Plain where the sonar systems went dark sits above one of the least surveyed stretches of oceanic crust on Earth. The seafloor mapping coverage of the Central Pacific is, even by the generous standards of a global seafloor that is less than 25% mapped at meaningful resolution, remarkably sparse. The surveys that do exist for the target region were conducted primarily in the 1970s and 1980s using single-beam sonar technology that produced trackline data, meaning the seafloor was mapped only directly beneath the ship's path, with gaps between tracks of tens of kilometers in some cases. The interpolated charts that exist for the region are largely the product of filling those gaps with smoothed estimates based on gravitational anomaly data collected by satellites, which provides a low-resolution proxy for seafloor topography, but which misses features smaller than approximately 10 kilometers in horizontal extent, and which has limited sensitivity to the kind of subtle topographic complexity that is relevant to understanding the geological context of the target region. What the existing charts show is a broad, relatively flat abyssal plain interrupted by a small number of isolated seamounts and a low-relief ridge system in the eastern portion of the target area, whose origin and age are poorly constrained by the available data. What the existing charts do not show, because the resolution of the surveys from which they were derived is insufficient to reveal it, is the detail of the seafloor fabric at the scale of hundreds of meters, the scale at which hydrothermal circulation systems, sediment deformation features, fault systems, and biological community distributions are visible and interpretable. The target region has never been surveyed with modern multi-beam sonar technology at the resolution required to produce a seafloor map comparable to what is routinely available for geologically interesting areas of the mid-ocean ridge system or the continental margins. It has been assumed on the basis of low-resolution data and the geological reasoning that the Central Pacific crust in that area is old, cold, and tectonically inactive to be unremarkable. The assumption of unremarkability is the same assumption that allowed the methane venting field identified in last year's investigation to go undetected until an independent researcher noticed something odd in acoustic data. It is the assumption that the deep ocean, in places that have not attracted focused scientific attention, is doing what the models predict it should be doing. It is an assumption with a poor track record. The geological history of the crust beneath the target region is, to the extent it can be reconstructed from the available data, more complex than the low-resolution charts suggest. The Pacific Plate in that region is estimated to be between 80 and 110 million years old, formed at a mid-ocean ridge that has long since migrated away, and it has been moving slowly northwestward ever since, carrying the sediment pile that has accumulated on its surface and the chemical and thermal legacy of its formation and subsequent cooling. Old oceanic crust is not geologically dead. It is geologically slow, but it continues to interact with the seawater that percolates through it, exchanging heat and chemistry in processes that operate on timescales of millions of years, and that are collectively important to the global cycling of elements including carbon, sulfur, and iron. In certain configurations, old oceanic crust that has been subject to bending stresses as it approaches a subduction zone develops networks of normal faults that allow seawater to penetrate deeper into the crust than normal, enabling a type of water-rock reaction called serpentinization that produces hydrogen gas and heat as byproducts. The target region is not immediately adjacent to a subduction zone, but the Pacific Plate's trajectory carries it toward the western Pacific Trench systems, and the stress state of the plate in the target region, while not well characterized because the seismic monitoring network in that part of the ocean is sparse, may include deformation features that are not visible in the existing geological data. There is a specific geological feature in the target region that has received attention in the technical discussions now. Circulating among researchers, a low-relief ridge system in the eastern portion of the target area that appears in the low-resolution bathymetric data as a subtle topographic high extending roughly east-west for approximately 400 kilometers. The origin of this ridge is uncertain. It has been tentatively attributed in the literature to a fossil spreading center, a section of mid-ocean ridge that became tectonically inactive millions of years ago and was subsequently buried under the accumulating sediment blanket. Fossil spreading centers are geologically interesting because they can retain residual hydrothermal activity, low-temperature diffuse fluid flow driven by the cooling of residual magmatic heat for tens of millions of years after active spreading ceases. They also represent zones of crustal weakness where faulting and fracturing can allow fluid communication between the deep crust and the overlying sediment column, providing pathways for the migration of methane and other gases from deep geological sources toward the seafloor and into the water column. If the low-relief ridge in the eastern target area is indeed a fossil spreading center, and if it retains sufficient residual thermal activity to drive fluid flow through the overlying sediment, then the combination of geological substrate and the thermal and acoustic anomalies identified in the pre-blackout data acquires a coherence that the flat abyssal plain interpretation of the target region does not provide. The ridge would be the heat source. The fluid flow through the sediment would be the mechanism delivering warm, chemically altered water to the base of the hydrate stability zone. The hydrate destabilization at the margin of the stability field would be the process releasing methane into the water column. And the methane in the water column, if released at sufficient rate and over sufficient area, would be the acoustic scattering medium responsible for the sonar blackout. This chain of inference is not established fact. Each link in the chain has uncertainty attached to it, and the chain as a whole has not been subjected to the kind of systematic testing that would be required to move it from hypothesis to finding. But it is internally consistent. It is consistent with the available data from multiple independent sources, and it identifies a specific geological mechanism that is grounded in documented processes operating in analogous settings elsewhere in the ocean. The fossil spreading center hypothesis is the most complete geological explanation currently on the table for the sequence of events leading to the sonar blackout, and its completeness, its capacity to connect the thermal anomaly to the current anomaly to the acoustic anomaly to the blackout through a chain of known physical processes, is why the researchers who have assembled it are taking it seriously, even though confirming it would require a level of direct geological investigation of the target region that has not yet been conducted. What makes the hypothesis more than an interesting geological story? What gives it the weight that has caused 3 federal agencies to be involved in the response to the blackout and that caused the pre-blackout data to be flagged for interagency review before the blackout even occurred, is the scale of the methane release that the hypothesis implies. If a fossil spreading center of the apparent dimensions of the eastern target area ridge is driving hydrate destabilization across the full geographic extent of the sonar blackout, the area of active methane release into the water column may be unprecedented in the documented record of marine methane seep systems. The largest known methane seep fields in the ocean, systems like the Coal Oil Point seep field off Santa Barbara or the extensive seep systems along the Cascadia margin, cover areas of tens to hundreds of square kilometers. The target area of the sonar blackout covers hundreds of thousands of square kilometers. Even if only a fraction of that area is actively venting, the scale of the potential methane flux into the water column and the fraction of that flux that might reach the atmosphere is a number that climate scientists and carbon budget researchers would find extremely significant, and that the agencies involved in managing the public communication of the event would find extremely difficult to present without causing the kind of public alarm that makes the management of subsequent information considerably more complicated. The scale is the reason for the careful language. The scale is the reason for the thermocline disruption explanation. The scale is the reason 3 agencies are involved in a response to what is officially being described as an instrument anomaly. And the scale, if the hypothesis is correct, is the reason that what is happening in the dark water column of the Central Pacific matters to every person on this planet who breathes air that has been regulated for 10,000 years by a climate system that depends on the ocean staying approximately where it is in its carbon cycle. If you are still with this, and you want to understand what the scale of the implied methane flux actually means for the climate system and what the researchers who have run those numbers privately are saying about the timeline of potential atmospheric impact, subscribe now, because the next section is where this story moves from the ocean floor to the global atmosphere, and the numbers involved are the kind that change the framing of every other conversation about climate that you have heard. The numbers that connect a large-scale seafloor methane release event to the global atmosphere are not simple numbers, and presenting them honestly requires distinguishing carefully between what is measured, what is modeled, and what is inferred, because the difference between those 3 categories is the difference between a finding and a projection and a speculation, and collapsing that distinction in either direction, toward false certainty or toward false dismissal, produces a picture that is less accurate and less useful than the one the data actually supports. With that framing established, here is what the available science says about the pathway from seafloor methane to atmospheric consequence, and here is where the numbers attached to the target region sit within that pathway. Methane released from the seafloor at abyssal depths does not travel directly to the atmosphere. The water column intervenes, and the water column is not a passive conduit. It is a reactive medium in which methane undergoes a set of transformations that determine how much of what leaves the seafloor ultimately reaches the sea surface and enters the atmosphere above it. The primary transformation is microbial oxidation. The deep ocean contains communities of methane-oxidizing microorganisms, bacteria and archaea, that use dissolved methane as an energy source, converting it to carbon dioxide in the process. These microbial communities are remarkably effective at consuming methane in the water column, and in many documented seep systems, the majority of the methane released at the seafloor is oxidized before it reaches the surface. The efficiency of microbial oxidation depends on several factors: the rate of methane supply relative to the abundance of the oxidizing community, the residence time of the methane-enriched water in the water column before it reaches the surface, and the availability of the electron acceptors, primarily sulfate and oxygen, that the oxidation reactions require. In the deep ocean, where residence times are long and the methane supply from most seep systems is modest, relative to the oxidizing capacity of the microbial community, methane oxidation is highly efficient. Most of what is released at the seafloor is consumed in the water column, and the atmospheric signal from even large deep-water seep systems is small. This efficiency of deep-water methane oxidation has historically been one of the main reasons that the scientific community has treated seafloor methane release as a significant biogeochemical process, but not as an immediate atmospheric threat. The ocean's microbial community is a buffer, and it has been a reliable one. The qualifier that changes this picture is rate. Microbial oxidation, like any biological process, has a capacity limit. The microbial communities that consume methane in the water column are sized, in terms of their abundance and their metabolic rate, to handle the methane supply that the system has historically delivered. If the methane supply increases suddenly and dramatically, faster than the microbial community can respond by growing its population and upregulating its metabolic activity, the oxidation buffer is overwhelmed. Methane that would normally be consumed in the water column passes through unreacted, reaching the sea surface and entering the atmosphere. The timescale on which the microbial community can respond to an increase in methane supply the time required for the population to grow and the metabolic capacity to scale up, is measured in weeks to months, not hours to days. If the methane release implied by the Sonar blackout data is occurring at rates significantly above what the existing microbial community of the target region's water column was sized to handle, then the buffer is operating under conditions it was not calibrated for. And the efficiency of methane oxidation in that water column may be significantly lower than the deep ocean average. The methane that gets through the buffer, that reaches the sea surface and enters the atmosphere, is immediately relevant to the global climate in a way that is determined by two factors: the quantity of methane entering the atmosphere and the timescale over which it does so. Methane is a greenhouse gas with a global warming potential approximately 80 times that of carbon dioxide over a 20-year timescale and approximately 30 times that of carbon dioxide over a 100-year timescale. The difference between those two numbers reflects the fact that methane is chemically reactive in the atmosphere and is destroyed by reaction with the hydroxyl radical over a timescale of roughly a decade, converting to carbon dioxide and water in the process. This means that methane's short-term warming impact is large, and its long-term impact, while still significant, is smaller as the methane is progressively converted. From a climate policy perspective, the 20-year global warming potential is the more operationally relevant number, because the climate feedback timescales of most concern, the ones that could trigger non-linear responses in the Earth system, operate on decadal rather than centennial timescales. A large pulse of methane into the atmosphere over a period of months to years would have a disproportionate short-term warming effect relative to an equivalent mass of carbon dioxide. And that short-term warming effect could, in principle, accelerate other climate feedbacks that are themselves sensitive to temperature on decadal timescales. The Arctic permafrost feedback, in which warming causes permafrost thaw that releases additional methane and carbon dioxide, amplifying the warming that caused the thaw. The ice albedo feedback, in which warming reduces ice cover, increasing the absorption of solar radiation by the darker ocean surface beneath it, further amplifying warming. These feedbacks are not hypothetical. They are operating now at measurable rates, and their sensitivity to additional methane forcing is a subject of active research. The numbers attached specifically to the target region require honest qualification because they are derived from estimates with large uncertainty ranges. The area of the Sonar blackout, approximately the size of Texas, provides a geographic constraint on the potential scale of the methane release. The acoustic characteristics of the blackout, specifically the total signal loss rather than partial attenuation, provide a lower bound on the gas bubble density in the water column, and from that lower bound, a lower bound on the methane flux from the seafloor can be estimated. The pre-blackout thermal anomaly in the Argo float data provides a constraint on the temperature perturbation at depth, and from that perturbation, a rough estimate of the volume of hydrate that may have been pushed outside its stability field can be derived. When these constraints are combined, using the conservative end of the uncertainty ranges at each step, the implied methane flux from the target region is in the range of tens of millions of tons per year, with the upper end of the uncertainty range extending significantly higher. For comparison, the total global oceanic methane flux to the atmosphere under normal conditions is estimated at approximately 10 to 15 million tons per year. The lower bound of the estimate for the target region alone, under the fossil spreading center and hydrate destabilization hypothesis, approaches or exceeds the normal global oceanic methane flux in its entirety. That comparison is not presented to manufacture alarm. It is presented to communicate scale, because scale is what the official thermocline disruption explanation obscures, and scale is what makes the interagency response to the blackout comprehensible. If the fossil spreading center hypothesis is correct, if the numbers at even their conservative end are approximately right, then what is happening in the dark water column of the Central Pacific is not a regional oceanographic anomaly with local biogeochemical significance. It is a global carbon cycle event of a magnitude that the monitoring systems, the climate models, and the policy frameworks currently in operation were not designed to detect, represent, or respond to. The researchers who have assembled these estimates privately are not publishing them. They are sharing them in the careful, informal channels of scientific communication that precede formal publication, through email and conference calls, and the kind of intense, focused conversation that happens when people who have spent their careers preparing for a specific class of problem suddenly find themselves looking at data that suggests that problem may be occurring. They are not publishing because the estimates have large uncertainty ranges, and because the data supporting the hypothesis is preliminary, and because the professional and institutional consequences of publishing a claim of this magnitude without the evidentiary foundation to fully support it are severe in ways that anyone who has watched careers damaged by premature high-profile claims in controversial areas of science will recognize immediately. The caution is rational. It is also from the perspective of the public, whose understanding of what may be happening in the Central Pacific is currently shaped by the thermocline disruption explanation, a form of information delay that has consequences of its own. The gap between what the researchers are discussing privately and what the public is being told officially is not a conspiracy. It is the normal, painful, sometimes dangerous lag between what science finds and what institutions are prepared to communicate, playing out in real time over a section of ocean that has gone dark on every sonar system we have, and that is doing something in the dark that the available evidence suggests is very large and very important, and that nobody with the authority to tell the whole story is yet prepared to say out loud. The biological consequences of a large-scale methane release event in the Abyssal Pacific are a dimension of this story that has received almost no attention in the conversations currently circulating among the researchers involved, partly because the immediate focus has been on the physical and chemical characterization of the event, and partly because the deep-sea biology of the target region is so poorly documented that assessing biological consequences requires making assumptions about baseline community structure that the available data does not robustly support. But the biology matters, and it matters in ways that connect the deep ocean event to the surface world through pathways that are different from the atmospheric methane pathway and that operate on different timescales and through different mechanisms. Understanding those pathways requires understanding something about how the deep ocean's biological communities are structured and how they respond to the kind of chemical perturbation that a large-scale methane release would represent. The abyssal zone of the Central Pacific, under normal conditions, supports a sparse but functionally important biological community. The organisms living at those depths are adapted to the extreme conditions of the abyssal environment, near freezing temperatures, crushing pressure, near total darkness, and a food supply that consists almost entirely of the slow rain of organic particles sinking from the productive zones thousands of meters above. This material, called marine snow, is the primary energy source for most abyssal organisms, and its quantity is small. The Central Pacific Gyre, as an oligotrophic system, produces less marine snow than more productive ocean regions, which means the abyssal communities beneath it are particularly food-limited and particularly dependent on the consistency of whatever organic supply does reach them. The organisms that have adapted to this environment over millions of years of evolutionary time are not generalists equipped to handle rapid chemical changes in their surroundings. They are specialists, calibrated to a narrow range of conditions that has been stable for longer than most surface ecosystems have existed in their current form, A large-scale methane release into the water column above them would alter that chemical environment in ways that are potentially severe and potentially rapid. The most immediate chemical consequence of large-scale methane venting into the water column is oxygen depletion. The microbial oxidation of methane consumes dissolved oxygen, and in a water column with a large methane load, the oxygen demand from methane oxidation can exceed the supply of dissolved oxygen available, producing hypoxic or anoxic conditions, low oxygen or no oxygen water, in the layers where oxidation is occurring most intensively. The deep Pacific is not oxygen-rich under normal conditions. The oxygen minimum zone, that layer of the water column, where microbial respiration of sinking organic material has depleted dissolved oxygen to its lowest values, sits at depths between roughly 500 and 1,500 meters in much of the Pacific, and the water below it, while somewhat better oxygenated due to the intrusion of deep water masses formed at high latitudes, has oxygen concentrations that are lower than in the surface ocean and that provide less buffer against oxygen drawdown. If methane oxidation in the water column of the target region is consuming dissolved oxygen at the rate implied by the estimated methane flux, the oxygen concentration in the deep water column of that region may be declining, and the biological consequences of that decline for the abyssal and bathypelagic communities living in that water are potentially catastrophic on the timescales relevant to the organisms involved. Oxygen depletion in the deep water column does not kill organisms instantly. It kills them through a progressive physiological stress that begins with reduced metabolic efficiency, progresses to impaired reproduction and growth, and culminates in mortality when oxygen concentrations fall below the minimum required for aerobic metabolism. Different organisms have different oxygen tolerances, and the response of a diverse community to progressive oxygen depletion is a succession of biological changes. The loss of the most oxygen-sensitive species first, followed progressively by the loss of less sensitive ones, with the most tolerant anaerobic and microaerophilic organisms persisting longest and eventually coming to dominate the altered community. This succession, if it is occurring in the target region, would be happening in a biological community that has never been systematically surveyed, in water that is currently acoustically opaque to the monitoring systems that might otherwise detect its signals, in a section of ocean that has been assumed to be unremarkable and that has therefore attracted neither the monitoring resources nor the scientific attention that would be required to document what is being lost. The abyssal Pacific is not a biological desert, but its organisms are not charismatic and its ecosystems are not visible, and the combination of inaccessibility, invisibility, and low public salience means that biological changes of even significant magnitude in the deep Central Pacific could proceed for extended periods without entering the public consciousness or the policy conversation. The carbon cycle consequences of biological community disruption in the deep ocean are a second-order effect that operates through a mechanism called the biological pump. The biological pump is the process by which carbon fixed by photosynthesis in the surface ocean is transported to the deep ocean through the sinking of organic particles, the bodies and waste products of organisms that live in the sunlit upper ocean and die and sink, carrying their carbon with them into the depths where it is remineralized by deep-sea organisms and bacteria and returned to the dissolved inorganic carbon pool of the deep water. The biological pump is one of the ocean's primary carbon sequestration mechanisms, responsible for maintaining atmospheric carbon dioxide at lower levels than would exist if the ocean's biological productivity were absent. Its efficiency depends on the entire vertical ecosystem, from the phytoplankton in the surface layer that fix the carbon to the bacteria and animals in the deep that process the sinking particles. If the deep sea community that processes sinking organic material is disrupted by oxygen depletion associated with methane oxidation. The efficiency of the biological pump in the target region may decline, meaning that carbon that would normally be sequestered in the deep ocean is instead remineralized at shallower depths and returned to the atmosphere more rapidly. This is a biological feedback that amplifies the climate consequences of the initial methane release by reducing the ocean's capacity to sequester carbon at the same time as it is releasing methane from previously stable geological stores. The magnitude of this biological feedback in the target region is impossible to quantify with the available data, because the baseline biological community structure and the current state of oxygen depletion in the water column are both unknown, but its direction is not uncertain. Disruption of the deep sea community in a large-scale methane venting event tends to reduce the efficiency of the biological pump, and a reduction in biological pump efficiency is a positive climate feedback, meaning it amplifies warming rather than moderating it. The third biological dimension of this story is the one that is simultaneously the most speculative and the most potentially significant in terms of its implications for the surface world. The chemosynthetic biological communities that form around methane seep systems, the communities of tube worms, clams, mussels, bacterial mats, and associated organisms that derive their energy from the chemical reactions involving methane and sulfide rather than from photosynthesis, are among the most productive ecosystems in the deep ocean. They form dense, diverse communities in areas of active fluid flow, and they support food webs that extend upward through the water column as the organic material they produce is consumed and repackaged by mobile organisms that move between the seep communities and the surrounding deep-sea environment. If the target region is developing a large-scale chemosynthetic ecosystem in response to the methane flux from the seafloor, that ecosystem would represent a biological productivity anomaly in the least productive part of the Pacific Basin, an island, or more accurately a continent, of biological richness in the oligotrophic desert. The ecological implications of that anomaly for the wider Pacific food web through the trophic connections between the deep chemosynthetic ecosystem and the mid-water and surface communities above it are unknown. They have never been studied because a chemosynthetic ecosystem of the apparent scale implied by the methane flux estimates has never previously been documented. The deep ocean is rewriting its own biology in the dark water column of the Central Pacific, and the instruments that might document that rewriting are currently returning no signal, and the agencies responsible for monitoring the system have attributed the absence of signal to thermocline disruption, and the researchers who know better are being careful about what they say, and the public whose planet this is knows almost none of it. That gap between what is happening in the dark water and what the surface world understands to be happening there is not stable. Gaps of this kind do not stay closed indefinitely. The data continues to accumulate, the researchers continue to talk, the FOIA requests continue to be filed, and the ocean continues to do what it is doing, whether or not the surface world is paying attention to it. The question is not whether the gap closes. It is whether it closes fast enough for the information to be useful. The international dimension of the sonar blackout has received almost no attention in the conversations that have reached the public domain, and that absence is itself informative, because the target region of the Central Pacific is not a domestic issue in any meaningful sense. It is international waters, governed by the framework of the United Nations Convention on the Law of the Sea, monitored by assets belonging to multiple nations, and relevant to the climate obligations of every country that has signed the Paris Agreement, which is to say virtually every country on Earth. The fact that the public conversation about the blackout has been shaped almost entirely by a single American agency's explanation offered 14 hours after the event, without any visible coordination with the international scientific community or the international governance frameworks that have jurisdiction over the management of shared ocean resources, is a governance failure as significant as the monitoring failure that allowed the pre-blackout anomalies to go uncoordinated for 6 weeks. The nations with the most developed deep ocean monitoring capabilities in the Pacific, the United States, Japan, China, Australia, and to a lesser extent several European countries with research programs operating in the basin, all have assets that were potentially affected by or relevant to the blackout event, and the response from those nations in the days following the event has been, in the public record, essentially silent. Japan's Japan Agency for Marine Earth Science and Technology, which operates one of the most sophisticated deep-sea monitoring networks in the Western Pacific, including cabled seafloor observatory systems capable of continuous real-time monitoring of seismic, acoustic, pressure, and chemical parameters at abyssal depths, has not issued any public statement about the blackout or about anomalies in its own data from the target region. This silence is ambiguous. It could mean that JAMSTEC's systems, which are concentrated in the Western Pacific near Japan's continental margin, and the adjacent trench systems, do not have sufficient coverage of the Central Pacific target area to have detected the pre-blackout anomalies, or the blackout itself. It could mean that JAMSTEC has detected something in its data, but is coordinating its response with other agencies before making public statements. Or it could mean that JAMSTEC has been asked, through diplomatic or scientific channels, to defer to the lead agency managing the public communication of the event. Any of those three possibilities is consistent with the public record, and distinguishing between them requires access to the internal communications of an agency that does not make its internal communications public. What is known is that the informal scientific networks connecting JAMSTEC researchers to the independent researchers who have been analyzing the blackout data have been active since the event occurred, and that the conversations in those networks have not been characterized by the kind of surprise and disbelief that would be expected if JAMSTEC's own data showed nothing anomalous in the target region. China's ocean monitoring capabilities in the Pacific have expanded dramatically over the past decade, with the deployment of a network of autonomous underwater gliders, moored instrument arrays, and research vessels operating across the basin, and with a deep-sea research program that has conducted more Hadal expeditions in the past 5 years than any other nation. China does not publish its operational ocean monitoring data in the same open access frameworks that American and European agencies use, which means the question of what Chinese monitoring systems have detected in the target region is essentially unanswerable from publicly available information. But Chinese ocean researchers operate in the same international scientific community as their American and Japanese counterparts, attend the same conferences, publish in the same journals, and communicate through the same informal channels. And the signals coming through those channels suggest that the Chinese deep-sea research community is aware of the blackout and is treating it as a significant event rather than an instrument anomaly. The governance framework that should be managing the international response to a potentially significant deep ocean event in the Central Pacific is the framework established under UNCLOS and administered through a set of international bodies, including the International Seabed Authority, the Intergovernmental Oceanographic Commission of UNESCO, and the scientific committees of the World Meteorological Organization. These bodies have the mandate, in principle, to coordinate international scientific responses to anomalous ocean events, to facilitate data sharing between national monitoring programs, and to ensure that findings with global implications are communicated to the international community in a timely and transparent manner. In practice, the speed at which these bodies operate and the political constraints under which they function mean that coordinating an international response to a rapidly evolving ocean event is a slow and complicated process that is structurally unsuited to the timescales on which the science is developing. The Intergovernmental Oceanographic Commission has not issued any statement about the blackout. The International Seabed Authority, which has jurisdiction over the deep-sea mining applications in the target region that were discussed in the context of last year's venting field investigation, has not issued any statement. The machinery of international ocean governance is either unaware of the event, which seems unlikely given the assets and personnel involved, or is aware and has decided that the appropriate response at this stage is to monitor the situation through existing channels, while the lead national agency manages the public communication. Either way, the international governance gap is real, and it is a structural problem that predates the current event, and that the current event makes newly visible. The deep ocean is a global commons. What happens in it, at the scale implied by the blackout data, is a matter of global consequence. The governance frameworks that manage that commons were designed for a slower world, a world in which ocean events developed over timescales of decades, and in which the monitoring infrastructure was sufficient to provide adequate warning before consequences materialized. They were not designed for a world in which a significant fraction of the Pacific abyssal plain can go acoustically dark in a matter of hours, in which the pre-event anomalies are observed by independent researchers operating outside the institutional framework rather than by the monitoring agencies responsible for the region, and in which the public explanation offered by the responsible agency is inadequate to the data within hours of its issuance. The governance frameworks need updating, and updating them requires first acknowledging that they are inadequate, which requires first acknowledging that the event they are failing to govern is real and significant, which requires first acknowledging that the thermocline disruption explanation does not hold up. Each acknowledgement is a step that an institution has reasons not to take quickly, and the accumulation of those reasons across multiple institutions and multiple national jurisdictions is why the international response to the blackout has been, in the public record, essentially nothing. Meanwhile, the target region of the Central Pacific remains dark on every sonar system trained at it, and the methane, if the hypothesis is correct, continues to enter the water column, and the microbial buffer, if it is being overwhelmed, continues to be overwhelmed, and the deep-sea community, if it is being disrupted by oxygen depletion, continues to be disrupted. The ocean does not pause while the governance frameworks catch up. It continues doing what it is doing, at depth, in the dark, on its own schedule, indifferent to the institutional timelines and political constraints of the surface world that depends on it for the stability of its climate, the productivity of its fisheries, the regulation of its weather, and the continuation of the biogeochemical cycles that have made this planet habitable for the duration of human civilization. The governance gap and the monitoring gap and the communication gap are all expressions of the same underlying problem. The surface world has not built the relationship with the deep ocean that the deep ocean's importance to the surface world requires. That relationship, built on sustained attention, adequate resources, transparent communication, and international cooperation, is what the current event is demanding, and what the current institutional response is not providing. The researchers who are watching the blackout data and running the methane flux numbers and having the careful conversations in the informal channels of the scientific community are not asking for alarm. They are asking for attention, for resources, for the kind of serious, sustained, well-funded international scientific engagement with the deep Pacific that the available evidence now clearly justifies. That ask is reasonable. It is urgent, and it is not currently being met. The question that everyone who has followed this story to this point is entitled to ask, and that deserves a direct and honest answer rather than a deflection into further technical detail, is this: what does the sonar blackout in the Central Pacific mean for the people living on the surface of this planet? And on what timeline do the implications, if the fossil spreading center and hydrate destabilization hypothesis is correct, become tangible in ways that affect daily life rather than existing only in the data streams of oceanographic monitoring systems and the private conversations of deep-sea researchers? The honest answer to that question has several layers, and each layer requires distinguishing between what the evidence currently supports, what the models project under various scenarios, and what the genuine uncertainties are, because collapsing those distinctions in the direction of either reassurance or alarm produces a picture that is less accurate and less useful than the one the actual state of knowledge provides. The first layer of the answer is atmospheric, and it operates on the shortest timescale. If the methane flux from the target region is occurring at the rates implied by the conservative end of the estimates derived from the blackout data, and if the microbial oxidation buffer in the water column is being overwhelmed by the rate of supply, then methane is entering the Pacific atmosphere above the target region at rates that are anomalous relative to the background flux. Atmospheric methane concentrations are monitored continuously by a global network of stations maintained by NOAA's Global Monitoring Laboratory, and the data from those stations is publicly available in near real time. The stations closest to the target region, located on Mauna Loa in Hawaii and at several Pacific Island locations, have been showing a pattern in their methane data over the past several weeks that has attracted attention from researchers who monitor the global methane budget. The pattern is not dramatic in absolute terms. The methane concentrations at those stations have not spiked to values that would immediately register as anomalous to a casual observer of the data. What they have shown is a persistent, slight elevation above the seasonal baseline that is consistent in its timing with the onset of the pre-blackout anomalies in the ocean data, and that has not been attributed to any identified local or regional source. Atmospheric methane monitoring is a mature science with well-characterized source attribution methods, and the researchers who have been looking at the Pacific Station data in the context of the blackout have noted that the slight elevation is consistent in its isotopic signature with a marine biogenic methane source, meaning methane produced by microbial processes in marine sediments rather than methane from thermogenic or anthropogenic sources. The isotopic signature alone does not confirm the target region as the source. Isotopic signatures identify source type, not source location, and marine biogenic methane sources are distributed across the global ocean. But the combination of timing, geographic proximity of the monitoring stations to the target region, and isotopic consistency with a marine sediment methane source is a set of constraints that makes the target region a plausible contributor to the atmospheric signal, and the researchers who have assembled this analysis are treating it as a piece of corroborating evidence for the hypothesis rather than as an independent confirmation of it. The atmospheric layer of the answer connects to the second layer, which is the climate feedback layer, and which operates on a longer timescale measured in years to decades rather than weeks to months. The relationship between an anomalous methane flux from the Pacific seafloor and the global climate is not a simple linear one. It is mediated by the chemical lifetime of methane in the atmosphere, by the capacity of the atmospheric hydroxyl radical sink to process the additional methane load, and by the sensitivity of the climate system to the additional radiative forcing that the methane represents. Under normal conditions, the atmospheric methane burden is in approximate steady state with sources and sinks roughly balanced. An anomalous source of the scale implied by the blackout hypothesis would represent a perturbation to that steady state, pushing the methane burden higher and increasing the radiative forcing on the climate system. The magnitude of the climate response to that perturbation depends on the duration of the anomalous flux and the sensitivity of the climate system at its current state, which is already warmer and more energetically loaded than at any point in the past several thousand years. The climate feedback layer is where the numbers become genuinely difficult to sit with, because the sensitivity of the climate system to methane forcing is not a fixed value. It varies with the state of other climate feedbacks that are themselves sensitive to temperature, and the current state of those feedbacks, with Arctic sea ice declining, permafrost thawing, and the deep ocean accumulating heat at rates unprecedented in the instrumental record, means that the climate system's sensitivity to an additional methane forcing may be higher than historical averages would suggest. The researchers who have run these numbers in the context of the blackout hypothesis have not published their results. The results exist in the form of model runs conducted on institutional computing infrastructure, shared informally between the researchers involved and described in the careful language of preliminary analysis rather than in the formal language of published findings. What those model runs show, at the conservative end of the methane flux estimates and using climate sensitivities consistent with the current consensus range, is a potential contribution to global mean temperature over the next 20 years that is small in absolute terms, measured in hundredths of a degree Celsius, but that is additive to the trajectory the climate system is already on, and that, combined with the other feedbacks currently operating, could contribute meaningfully to the probability of crossing temperature thresholds that the international community has identified as significant. The third layer of the answer is the one that operates on the longest timescale, and that has the most uncertain but potentially most consequential implications. It is the question of whether the event in the target region is an isolated occurrence, a localized destabilization of a specific hydrate system driven by a specific geological forcing, or whether it is an early indicator of a more widespread process beginning to operate across the Pacific hydrate system as the deep ocean accumulates heat from above and geological forcing from below simultaneously. This question cannot be answered with the available data. It requires the kind of systematic, basin-wide deep ocean survey that does not currently exist and that would take years to conduct even if the resources were immediately committed. What can be said is that the conditions that the fossil spreading center hypothesis identifies as the driver of the target region event, specifically the combination of residual geological heat from crustal features and warming of the overlying water column from above, are not unique to the target region. Similar geological features, fossil spreading centers, seamount chains, fracture zones with residual thermal activity exist throughout the Pacific Basin, in most cases as poorly characterized as the eastern target area ridge that the hypothesis identifies as the geological driver of the current event. If a warming deep ocean is beginning to interact with these geological features in ways that drive hydrate destabilization at their margins, the target region may be the first location where the interaction has reached the threshold of detectability, but it is unlikely to be the only location where the interaction is occurring. The implication of that possibility, that the target region event is the leading edge of a more distributed process rather than an isolated occurrence, is the one that the climate researchers involved in the informal analysis network are most reluctant to articulate publicly, because articulating it requires making claims that go beyond what the current data can support and that carry the risk of being wrong in ways that are professionally and institutionally costly. But the possibility is real, and it is being discussed, and the data from the atmospheric methane monitoring stations, the pre-blackout ocean anomalies, and the sonar blackout itself are being examined in the context of that possibility by people who understand what it would mean if it were confirmed. What it would mean, in the plainest possible language, is that the deep Pacific hydrate system, which contains carbon stores estimated at roughly twice the total carbon in all other fossil fuel reserves combined, has begun a destabilization process that is being driven simultaneously by warming from above and geological forcing from below, that is occurring in regions that our monitoring infrastructure was not designed to detect it, that is, producing atmospheric methane signals that are currently below the threshold of immediate alarm, but that are consistent with the early stages of a process that could, if it continues and expands, represent a climate feedback of a magnitude and speed that the current policy frameworks and technological responses were not designed to manage. That is the worst-case reading of the available evidence. It is not the only reading. The evidence is preliminary. The hypothesis is unconfirmed. The uncertainty ranges are large, and the history of climate science includes many cases where preliminary findings of alarming implication turned out, on further investigation, to have more benign explanations. The appropriate response to the current state of knowledge is not panic. It is urgency, the specific kind of urgency that attaches to a situation where the potential consequences of inaction are severe, and the window for effective response may be closing faster than the institutional machinery of science and governance is currently moving. Urgency about getting the monitoring in place. Urgency about conducting the deep-sea surveys that could confirm or refute the hypothesis. Urgency about updating the climate models to incorporate the possibility of accelerated deep ocean methane release. And urgency about having the honest public conversation about what the data shows, which is what this story is attempting to be, with all of its qualifications and uncertainties intact. Because the qualifications and uncertainties are part of the truth, and the truth, in its full and complicated form, is what the surface world needs to understand what may be happening in the dark water below. The sonar systems monitoring the Central Pacific Abyssal Zone are still dark, not partially restored, not intermittently returning signal, not showing the gradual recovery that would be expected if the official thermocline disruption explanation were accurate and the disruption were dissipating in the normal way that thermocline disturbances dissipate through the slow processes of thermal diffusion and current-driven mixing that operate on timescales of days to weeks. Still dark, uniformly, across the full geographic extent of the target region, with the same sharp boundary that characterized the blackout from its first detection 11 days ago and counting in a section of ocean the size of Texas that has gone completely silent on every instrument trained at it, and that the responsible agency has described as an instrument calibration issue. The persistence is the most important single fact in this story at its current stage, because persistence is what distinguishes an event from a condition. And the distinction between those two categories is the difference between something that happened and something that is happening, between a phenomenon with a beginning and an end, and a phenomenon with a beginning that has not yet revealed its end. Events resolve, conditions endure, and what the 11-day persistence of the sonar blackout tells every researcher who understands the physics of the possible explanations is that this is a condition, not an event, that whatever physical process is responsible for the acoustic opacity of the target region's water column is not dissipating, is not moving, is not evolving in the ways that transient phenomena evolve, and that the word still, applied to the darkness in the Central Pacific, is the most scientifically significant word in any description of the current situation. The researchers who have been following this story from the beginning, who assembled the pre-blackout anomaly data from 3 independent instrument networks, and who have been running the methane flux estimates and the climate model scenarios in the informal analytical network that has formed around this event, are in a position now that is professionally and personally uncomfortable in ways that are worth acknowledging, because the human dimension of what it means to be a scientist confronting data of this potential significance is part of the story that rarely gets told, and that shapes the pace and the character of the public information flow in ways that are consequential. These are people who chose careers in ocean science because the ocean is vast and complex and full of things that are not yet understood, and who have spent years or decades building the technical expertise and institutional relationships required to do serious work at the frontier of what is known about the deep sea. They are people who understand, from from long experience that the most important discipline in confronting anomalous data is patience. The willingness to resist the pull of premature interpretation and to let the evidence accumulate to the point where conclusions can be drawn with appropriate confidence. They are people who have seen careers damaged by high-profile claims that turned out to be wrong, and who carry that institutional memory as a professional caution that is rational and appropriate, and that shapes how quickly and how publicly they are willing to commit to interpretations of data that fall outside the established literature. And they are people who are now sitting with a data set that is, in the assessment of the most experienced among them, unlike anything they have previously encountered in their professional lives, and who are having the careful, private, increasingly urgent conversations that precede the point at which the scientific community collectively decides that the evidence has accumulated to the threshold required for public commitment to a position. That threshold has not yet been crossed. The formal scientific response to the blackout, the peer-reviewed publications and the official agency reports, and the international scientific body statements that represent the authorized voice of the discipline, has not yet materialized in a form that matches the significance of the data. It is coming. The preprints are being written. The expedition proposals are being drafted. The data sharing agreements are being negotiated. The process of formal science is moving as it always moves, carefully and thoroughly and more slowly than the event it is documenting. In the meantime, the ocean does not wait. It is doing what it is doing. In the dark, at depth, in the abyssal zone of the Central Pacific, where every sonar system has gone silent, and where something large enough to absorb the acoustic energy of an entire monitoring infrastructure is maintaining itself with a coherence and a persistence that the available physical explanations are struggling to account for. The surface world is going about its business above it, largely unaware that anything unusual is occurring below, because the official explanation has provided a sufficient narrative for those who do not have the technical background to evaluate it. And because the researchers who do have that background are in the careful pre-publication stage of their analysis, and because the media landscape is not structured to give sustained attention to a story that does not resolve into a headline, that does not have a villain or a hero or a conclusion, that lives in the space between preliminary and confirmed, and that requires the kind of patient, technically grounded attention that this channel is committed to providing. What comes next in this story will be determined by several converging timelines. The timeline of the scientific analysis, which is moving toward publication of the pre-blackout anomaly data, and the blackout characterization in forms that will subject them to formal peer review, and that will, if the findings hold up under that scrutiny, establish the evidentiary foundation for the stronger claims about methane flux and climate implications that the informal network is currently discussing. The timeline of the expedition planning, which is proceeding in parallel with the analysis, and which, if funding is secured and permits are granted without the kind of interagency delay that affected last year's expedition to the methane venting field, could put a research vessel over the target region with deep-rated autonomous vehicles and ocean bottom seismometers and water column chemistry sensors within the next 6 to 12 months. The timeline of the monitoring data, which continues to accumulate from the Argo floats and the atmospheric methane stations and the current meter arrays and the hydrophone networks, adding daily to the dataset that the researchers are analyzing, and that is either building the evidentiary case for the hypothesis or accumulating the anomalies that will eventually force a revision of it. And the timeline of institutional response, the slowest and most uncertain of the four, which will eventually produce either a more adequate public explanation of the blackout than the thermocline disruption narrative, or a continuation of the current communication gap that will close, as communication gaps always do, not through deliberate institutional decision, but through the accumulation of evidence beyond the point where the gap can be maintained. The ocean is the largest system on this planet and the least understood, and what it is doing in its darkest and deepest layers is consequential for every living thing on the surface above it. And the story of the Central Pacific Sonar blackout is a story about that consequence, about the gap between what the ocean is doing and what the surface world knows it is doing, about the monitoring systems that are insufficient and the governance frameworks that are slow, and the institutional communication that is inadequate, and the individual researchers who are doing the work of looking honestly at data that does not fit the established frameworks and reporting what they find with the precision and the care and the professional courage that serious science requires. This channel will stay with this story. When the expedition data comes back, we will be here. When the preprints are posted, we will analyze them. When the atmospheric methane data shows the next anomaly, we will contextualize it against everything that has been assembled here. The Deep Pacific is not finished telling us what it contains, and we are not finished listening. If you have stayed with this story from its beginning to this point, you have done something that the architecture of the modern information environment actively discourages. You have given sustained, patient attention to a complicated, unresolved, genuinely important story that does not offer the satisfaction of a clean conclusion because the clean conclusion has not yet arrived. That attention is not passive. It is a form of participation in the process by which the public understanding of consequential scientific questions develops, and it is the foundation on which the pressure for adequate monitoring, honest communication, and serious institutional response is built. The ocean is dark on our sonar systems. The official explanation does not hold up. The researchers who know that are talking to each other in the careful language of people who understand what they are looking at. And the most important question is not what is in the dark water. The most important question is whether the surface world builds the relationship with its own ocean that the ocean's importance demands before the dark water tells us what it contains in a language that is impossible to misinterpret and too late to prepare for. Subscribe. Stay close to this story, and remember that the ocean covers 71% of this planet, reaches to depths that dwarf the height of every mountain on its surface, and has been doing things in its deepest layers since long before the first human being looked at its surface and decided it was mostly empty. It was never empty. It is not empty now. And what it is full of, in the dark zone beneath the Central Pacific, where every sonar system has gone silent, is something the surface world needs to understand before the silence ends.